Hello guys, welcome back to the series of lectures on big data. In the previous lecture, we learned what is big data. Today, we are diving into the Hadoop ecosystem, a game changer in the world of big data. If you have ever wondered how massive data sets are stored, processed, and analyzed, you are in the right place. Hadoop is like a superhero team of tools working together to tackle big data challenges. So let's explore what makes Hadoop so powerful. Meet Apache Hadoop, the heart of big data processing. Hadoop was created in 2005 by Doug Cutting and Mike Caffarella. Hadoop is an open source framework inspired by Google's file system and MapReduce. It was donated to the Apache Software Foundation in 2006. Apache Software Foundation is a non-profit supporting open source projects since 1999. There is a fun fact here about the name of Hadoop. Doug Cutting chose the name of Hadoop for a few specific reasons. Firstly, he wanted a name that did not have any particular meaning, so it won't limit the project scope as it evolved. This allowed the software to grow and change without being constrained by its name. Secondly, the name Hadoop was the name of a toy elephant owned by his son, so this personal touch made the name memorable and unique. Hadoop leveraged MapReduce from Google Framework and Hadoop distributed file system to handle big data efficiently. MapReduce breaks down applications into numerous small tasks, distributing them across a cluster. HDFS ensures data reliability and availability by replicating data blocks across multiple nodes within the cluster. This allows MapReduce to process data locally where it is stored, and in this way, they can enhance processing speed and also fault tolerance. Hadoop aims to operate efficiently on very large clusters, potentially scaling up to 10,000 nodes. Think of it as a super efficient library, storing and processing petabytes of data easily. Let's dive deeper. HDFS offers redundant and fault-tolerant storage by copying data across nodes. If one fails, there won't be a problem. Hadoop's parallel computation framework splits tasks for fast processing, and job coordination manages everything from scheduling to executing tasks like mapping and reducing. For developers, Hadoop takes away a headache of worrying about file location, failure, or scaling. It's like having a team of assistants handling the heavy lifting so you can focus on coding. Why is Hadoop so popular? Because it's scalable. It can handle petabytes of data effortlessly. It's economical, running on affordable commodity hardware. Think thousands of regular PCs. It's efficient, processing data where it is stored to save time. And it is reliable, keeping multiple data copies and redeploying tasks if something fails. These perks make Hadoop a top choice for big data, and we will see it in action next. Let's talk real-world impact. Yahoo has been a Hadoop pioneer, running massive clusters with tens of thousands of nodes managing hundreds of petabytes data. Their 16 clusters with over 35,000 servers handle everything from storage to deep learning models. By mixing old and new processors, Yahoo maximizes efficiency. This setup powers complex machine learning and analytics, proving Hadoop scalability in one of the largest deployments out there. Here is another application. The New York Times used Hadoop to digitize 11 million articles from 1851 onward. They converted 4 terabytes of TIFF images into PDFs using Hadoop on Amazon EC2 and S3. The kicker, it took less than 24 hours and it cost only $240. This project shows how Hadoop makes massive tasks fast and affordable, bringing history online for everyone to access. Hadoop's power comes from its core components. The core components are Hadoop Command, Hadoop Distributed File System, Hadoop Yarn, and Hadoop MapReduce. Hadoop Command provides essential libraries. HDFS stores huge datasets across clusters. Yarn manages resources, supporting batch processing with MapReduce, interactive queries with Tez, or in-memory processing with Spark. Finally, MapReduce handles batch jobs through map, shuffle, and reduce phases. Together, these make Hadoop a robust software for big data. The Hadoop ecosystem is a comprehensive framework designed to store, process, and analyze large data sets efficiently. Hadoop comprises several key components, each serving distinct functionalities. Hadoop ecosystem has several members like HDFS, MapReduce, Yarn, Flume, Kafka, Zookeeper, Impala, Spark, Oozie, Sqoop, Peak, Hive, HBase, Solr, Hive, etc. Imagine the Hadoop ecosystem as a bustling and futuristic library. In this library, each tool plays a unique role, like librarian, assistant, or system, keeping the library humming. HDFS is the library vast shelving system, storing books, or you can say data, securely and reliably across multiple stacks. MapReduce is a team of assistants who tackle big tasks by dividing them into smaller jobs, working in parallel to process requests efficiently. Yarn is the head librarian, assigning tasks and managing resources to ensure the library runs smoothly. Flume acts like conveyor belts, swiftly moving new books, or you can say data, from outside sources into the library's shelves. Kafka is the message board, passing notes between staff to keep everyone updated on new arrival and tasks. Zookeeper is the library coordinator, keeping track of who is doing what and ensuring all systems stay in sync. Impala is the speedy reference librarian, answering complex queries about books in seconds. Spark is the multitasking prodigy. Spark handles search, cataloging, and analytics all at once with blazing speed. Oozie is the scheduler, organizing workflow and ensuring tasks like restocking or cataloging happen on time. Sqoop is the delivery service, transferring books or data between the library database and external archives. Peak is the script writer, creating simple instructor for processing large collection of data. Hive is the friendly SQL expert, helping users query the library's catalog using familiar SQL language. HBase is the quick access disk, providing instant retrieval of specific books or records even from massive collection. Solr is the search specialist, offering fast and detailed search through the library vast index. And finally, Hive is the user-friendly front desk, making it easy for visitors to navigate the library's tools and services. Let's dive into how these roles bring the library to life. The first one is HDFS, Hadoop Distributed File System. HDFS is the Hadoop's storage backbone, solving big data challenges. So there are too many problems that HDFS is going to answer. Too much data for one machine? No problem. HDFS split it across many. Expensive hardware? Not a problem. It uses cheap commodity machines. Hardware failure? Not a problem. The smart software of HDFS handles them efficiently. Data loss? It's okay. It replicates data across nodes. Coordination issue? No problem. HDFS uses a master-slave setup. Like an elephant's memory, HDFS stores massive data sets reliably, making it a foundation of Hadoop's data management. The Hadoop Distributed File System, HDFS, is a distributed file system designed to run on commodity hardware. It shares many characteristics with existing distributed file systems, but also has significant differences. The HDFS is a distributed file system designed to run on commodity hardware, offering high fault tolerance and throughput for big datasets. HDFS relaxes some POSIX rules for faster streaming access. That's why it's perfect for large-scale applications. HDFS is cost-effective, scalable, and it can be integrated seamlessly with Hadoop's processing. HDFS design ensures data stays safe and accessible, even on low-cost hardware, making it a go-to for big data storage. The HDFS follows a master-slave architecture, and it includes two primary components, the name node and the data node. The name node acts as the master server, and it is responsible for managing the file system's metadata. They include metadata management, namespace management, and block management. In the case of metadata management, it keeps tracks of file names, directory structure, and file permissions. In the case of namespace management, it maintains the hierarchy of files and directories. And lastly, for the block management, it tracks which data nodes hold the replicas of each block. The data node functions as the slave in the HDFS architecture. Their responsibilities include data storage, heartbeat signals, and block reports. They store actual data blocks and regularly send heartbeats to the name node to confirm their availability. Periodically report the list of blocks they are storing to the name node, and regularly send heartbeats to the name node to confirm their availability. And they periodically report the list of blocks they are storing to the name node. This design ensures high fault tolerance, scalability, and efficient data processing. The name node stores metadata for files like the directory structure in a typical file system. The server holding the name node instance is quite crucial because we have only one of them. Transaction log for file deletions and additions or etc. does not use transaction for whole blocks or file systems, only for metadata. And also name node handles creation of more replica blocks when necessary, means after a data node failure. So once again, the name node stores metadata, like directory structure, and also manages operations like file addition without handling entire data blocks. The name node creates new replicas if data node fails. Data nodes store the actual data running on any file system like ext3 or NTFS, and also they report their blocks to the name node. With strategic replication, HDFS keeps data safe and accessible even during failures. The next component is Yarn. Yarn stands for Yet Another Resource Negotiator. This is a Hadoop resource manager. Yarn splits the old job tracker into the resource manager and application master. Resource manager allocates resources and the application master manages application lifecycles. Node managers replace task trackers. And in this way, they can handle resources on individual nodes using flexible containers. These containers have configurable memory, and that's why Yarn is more versatile and scalable for diverse workloads. Yarn manages cluster resources like memory and CPU, creating environment for Hadoop applications. Yarn deploys jobs, distributes code, and starts containers for execution. Yarn negotiates resources with applications, resolve conflicts, and assign tasks to queues with fair scheduling. The resource manager coordinates node manager which run executors locally. This setup ensures Hadoop applications run smoothly and efficiently across the cluster. The next one is MapReduce. MapReduce composed of map and reduce, two functions. The map function processes input pairs, emitting intermediate key value pairs. The reduce function combines these for each key, usually producing a single output. Like a mammoth tackling huge tasks, MapReduce breaks down data processing into parallel chunks, making it perfect for large-scale data crunching. MapReduce was introduced in a similar paper by Google in 2004. MapReduce is a high-level programming model and implementation designed for large-scale parallel design processing. MapReduce programming model consists of three parts: input and output, map function, and reduce function. Both input and output are represented as set of key and value pairs. Then the map function we defined as in key in value to list out key intermediate value process each input key value pair and emits a list of intermediate key value pairs based on the processing logic. Finally, we have reduce function. This is specified as out key list intermediate value into list out value. And this reduce function combines all intermediate values associated with a particular key and produces a set of merged output values. This model enables efficient processing of vast data sets in parallel, and it can leverage the distributed computing resources of large clusters. So let's see one example for MapReduce. We have input, the input is a text, and this text is in some sentences. So Hadoop is a big data framework. Hadoop can store vast data, Hadoop process big data, and etc. Several phases. The first phase is split. The input data is split into individual sentences to be processed. So each sentence is one. Then we have mapper phase. In the mapper phase, each sentence is processed by the mapper function, which output key value pairs. And in here, each word is a key and value is one, right? Then we have shuffle and sort. This phase groups all key value pairs by their keys. It means words, and each key corresponds to a list of values, right? 5 Hadoop and etc. here. In this reduce phase, the reduce function processes each group of key value pairs, combining the values. It means summing them to generate a single output value for each key. Then finally, we will have a final output, which is a list of words with their corresponding count or frequency. MapReduce can feel complex, so let's use an analogy, that is sorting coins. In the map phase, you can categorize coins by values, like 10 won, 100 won, 500 won, something like that, right? Then in the reduce phase, you count each pie in parallel using this machine. This mirrors how MapReduce processes data. It means splitting tasks, processing them concurrently, and combining results. It's like organizing a massive coin deposit in records, because when you want to deposit your coins, you cannot give them in mass, right? So this machine is going to separate them, count them, and finally give you one amount. So this is like two phases, mapper and reducers. Mapper categorize coin by their face values, like in this machine. Then the reducer count the coins in each face value in parallel. MapReduce is super versatile. It powers distributed grep to search patterns across files, URL access frequently to track website visits, and reverse web link graphs to map source to target URLs. MapReduce builds inverted indexes for search engine and handles distributed sorting of massive datasets. These applications show how MapReduce tackles diverse big data tasks easily. MapReduce is not perfect. MapReduce forces data into a rigid MapReduce structure, lacking support for operations like join or filter. It relies on disk-based HDFS, slowing things down with read and write operations. MapReduce is inefficient for iterative tasks like machine learning and only natively supports Java. Plus, it's limited to batch processing, not real-time or streaming. These limitations pave the way for tools like Spark, which we will explore soon. MapReduce uses disk-based data sharing, which ensures fault tolerance but slows things down. Spark, on the other hand, uses in-memory processing, slashing latency and excelling at iterative tasks like machine learning. Spark supports flexible operations and real-time processing, while MapReduce shines in batch jobs. Choosing between them depends on your needs. MapReduce for robust batch processing, Spark for speed and versatility. The next one is Kafka. Apache Kafka, our library's postal service, is a distributed streaming platform started by LinkedIn in 2011. Kafka handles real-time data streams in a replicated and partitioned cluster for scalability and fault tolerance. Kafka's topics are streams with multiple writers and readers, partitioned across nodes. Retention policies ensure data durability. With connectors for HDFS, JDBC, and Elasticsearch, Kafka is a reliable staging area for big data. Let's zoom into Kafka. Each topic is a data stream, partitioned for scalability and replicated for fault tolerance. Multiple writers and readers can access it simultaneously. Retention policies are based on time or size, keep data safe. Kafka integrates with systems like HDFS and Elasticsearch via connectors, making it perfect for real-time data processing in Hadoop's ecosystem. The next one is Flume. So traditionally, Flume is an open channel above ground using gravity to transport surface water. The same structure has been used by Apache Flume. Apache Flume is our data mover, like conveyor belts in the library. It's a distributed service for collecting and moving large log data volumes. Flume agents are easy to configure and extensible, and they are perfect for capturing web server logs, building complex data flows, or handling event-based data. With sources like logs, channel for staging, and things like HDFS, Flume creates robust data pipeline. Flume is all about streaming data with events containing meta headers and byte array bodies. These events can be filtered or aggregated. Flume's flexible and pluggable design supports custom sources, channels, and sinks. Flume ensures reliability with transactions. A Flume agent includes a source like Kafka or logs, a channel like memory, and a sink like HDFS, and all together make it a scalable data transport tool. Flume's data flow is super flexible. Agents can run on one machine or across a cluster. Data enters via sources like REST APIs, get processed by optional Java interceptors, staged in channels like Kafka, and lands in sync like HDFS. Flume supports consolidations. It means unifying data, and also aggregation, summarizing it for insights. This makes Flume a key player in streaming data pipelines. Consolidation refers to the process of combining separate items, entities, or data into a unified whole. Aggregation refers to the process of combining and summarizing multiple data points into a single value or set of values. For example, calculating the average, sum, or count of datasets. This is commonly used to obtain higher-level insight from raw data. The next one is Zookeeper. Zookeeper is like a manager who keeps track of the status of different operations in a library. Zookeeper ensures that tasks are coordinated and synchronized across the cluster. Apache Zookeeper is our library coordinator. The Zookeeper ensures tasks stay coordinated across Hadoop cluster. Zookeeper is an open source server for reliable distributed coordination, handling configuration management, group services, and task synchronization like leader election. Zookeeper's simple primitives enable complex services, keeping Hadoop's component in sync, just like a zookeeper managing animals in a zoo. The next one is Impala, like a super fast librarian who specializes in searching and retrieving specific information from the books. Impala provides real-time SQL queries on the data stored in the HDFS or HBase. Impala, as a massively parallel processing engine, it starts queries in just 100 milliseconds, way faster than Hive that we will study later. Impala was written in C++. It skips Java's overhead and does not use Yarn by default. Impala's speed makes it perfect for real-time analytics in Hadoop. Using Impala is easy. Impala uses Hive's meta store for table definitions. You map data, define tables, and run queries with interfaces like Impala Shell for command line, Hue for visuals, or JDBC or ODBC for applications. For example, an Impala SQL script can analyze a city's weather, cleaning data, and counting good weather days. Impala's speed and integration make it a data analyst's dream. The next one is Spark, like a multitasking librarian who can handle various types of tasks simultaneously. Spark can perform batch processing, real-time processing, and iterative processing efficiently. Apache Spark, our multitasking librarian, is a unified analytic engine since 2014. Spark is faster than MapReduce. It supports Python, Java, R, and Scala, and offers an interactive shell. Spark handles streaming, SQL, and analytics running on Hadoop or the cloud. Spark's versatility powers machine learning, data warehousing, and more, making it a big data superstar. So why Spark? MapReduce is slow for iterative or interactive tasks due to disk input, output, and limited operations. Spark's in-memory processing slashes latency and supports joins, filters, and more. Unlike specialized frameworks like Regel for graphs, Spark is a one-stop shop. Spark has RDD, resilient distributed datasets. Using these enable fault tolerance and parallel processing. These features make Spark a game changer. The core of Spark is resilient distributed datasets, or RDD. RDDs are immutable and partitioned data collections processed in parallel. RDDs are created for files or collections. RDDs support transformation like map or join and can be cached in memory for speed. They are fault tolerant and they can be used for recovering lost partitions. RDDs are shared across sparse components, and in this way, they enable flexible and high performance data processing. We have data containers. All the different processing components in Spark share the same abstraction called RDD. Spark offers RDDs for low-level control and data frames for structured data with schemas. Data frames are optimized and cached by Spark, built on RDDs for ease and performance. For example, data frame queries run faster due to Spark's optimizations. Whether you are a developer needing control or an analyst wanting SQL-like queries, Spark's got you covered. Spark operations are split into transformation and action. Transformations like map, filter, or join create new RDDs. Actions like count, collect, or save as text file return result to save data. These let you build complex workflow from sorting to aggregating, covering tasks like machine learning and streaming analytics. Spark's architecture is built for speed and flexibility. Spark offers APIs in Python, Java, R, and Scala with an optimized engine using directed acyclic graph for efficient execution. Unlike MapReduce two-stage model, Spark handles complex workflows. Tools like Spark SQL, MLE for machine learning, Spark Streaming, and GraphX for graphs make Spark ideal for streaming, analytics, and more. The next one is Oozie. Oozie is like task scheduler. Oozie helps in coordinating and managing workflow of different tasks in a library. For example, it can ensure that indexing of new books happens after they are added to the library. Apache Oozie is our task scheduler, coordinating Hadoop workflows. Oozie manages jobs like MapReduce, Hive, or Spark, defining dependencies and flow. The use cases for Oozie include ETL process, data pipelines, and data warehousing. For example, Oozie ensures new data is indexed only after it is added, so it can manage streaming complex multi-step tasks in Hadoop. The next one is Sqoop, like a bridge that connects your library to an external source. Sqoop facilitates the import and export of data between Hadoop and relational databases. Apache Sqoop is our bridge to relational databases like MS SQL, MySQL, or Oracle. Sqoop uses MapReduce for scalable data imports and exports. For big transfers, dedicated connectors optimize performance. Sqoop's integration makes moving data between Hadoop and databases a breeze. The next one is Peak, like a scriptwriter who writes programs to process data in Hadoop. Peak provides a high-level language for expressing data analysis programs. Apache Peak is our scriptwriter, and it simplifies data analysis with Peak Latin. Peak Latin is a high-level scripting language used in Apache Peak, and the goal is to simplify data processing and analysis on Hadoop. How? By transforming complex MapReduce tasks into concise and easy-to-write scripts. Peak is perfect for non-Java developers and rapid prototyping. Peak handles structured and unstructured data with a schema-on-read approach, making complex data processing accessible and efficient. The next one is Hive. Like a librarian who understands and speaks SQL, Hive provides a SQL-like interface to interact with the data stored in HDFS. So Apache Hive is our SQL-speaking librarian. Hive is a data warehousing solution. Hive uses HiveQL language. This language lets you query HDFS data translated into MapReduce or Spark jobs. Hive supports managed and external tables, excelling at batch processing and ad hoc reporting. While the job generated by Hive may not always be optimal, Hive's SQL-like interface is a hit for analysts. Apache Hive is a data warehousing solution built on top of Hadoop, providing an abstraction layer that facilitates queries and managing large datasets stored in HDFS. Hive enables users to interact with big data using HiveQL, and the HiveQL is like a SQL language designed for batch processing. This removes the need to write complex MapReduce programs directly because HiveQL queries are automatically translated into MapReduce. Using Hive is simple. Create a database, define tables on HDFS data, and run HiveQL queries. Tables can be partitioned for speed, and Hive supports formats like ORC or Parquet. Interfaces include command line, JDBC, ODBC, and Thrift API. For example, a HiveQL script can analyze the weather data, grouping results by data. Hive makes big data querying easy. The next one is HBase. HBase is like a special section in the library that provides random access to book, unlike HDFS, which is more suited for sequential access. Apache HBase is a scalable key-value store for low-latency read and write operations on large and sparse datasets. HBase is stored as sorted key-value pairs, and it is perfect for real-time analytics and quick lookups, integrating with HDFS for robust data management. HBase runs on HDFS using region-based and column familiarity partitioning. Raw keys are indexed for fast access, and data is stored as byte arrays. HBase supports updates, deletion, and binding like SQL and Python. The HBase master manages regions and metadata, while region servers handle data and recovery. HBase shines for concurrent random access, but it is not ideal for sequential processing. The HBase architecture consists of HBase master and region servers. The HBase master is responsible for managing the cluster and perform tasks such as assigning regions, it means partitions of a table, to region service, maintaining metadata, and managing table schemas. Region servers handle client requests for reading and writing data. They store the actual data in regions on HDFS, and they maintain the write ahead log or WAL for data recovery. Additionally, region servers perform region splitting when regions become too large, and in this way, they can ensure efficient data management and performance. The next one is Solr. Solr is like an advanced search engine in the library. Solr allows for efficient searching and indexing of documents. Apache Solr is our advanced search engine, using HDFS for index and log files without MapReduce. Solr integrates with Hadoop's authentication for secure nodes. Solr delivers fast, precise search on massive data, and in this way complementing Hadoop's storage and processing. Solr is like having a super smart librarian for quick information retrieval. The last one, but not least, is Hive. Hive is a user-friendly librarian's assistant. Hive provides a graphical user interface for interacting with various components of the Hadoop ecosystem. Hadoop User Experience, or Hive in short, is our friendly assistant. Hive is a web-based SQL editor for core Hadoop and Spark, and in this way enables us for self-service query. Hive is licensed under Apache 2.0 by Cloudera. Hive simplifies data exploration with its intuitive interface and so making it a go-to for analysts and engineers. And that's a wrap on the Hadoop ecosystem. From HDFS to Spark, Flume to Hive, we have seen how these tools work together to tame big data. Projects like Yahoo's Cluster and the New York Times Archive show Hadoop's real-world power. Thanks for watching, folks. If you have any questions in mind, please feel free to leave it as a comment below this video. Thank you and see you in the next lecture.